Welcome to another Geography 215 math video. This math video is for Chapter 7. The objectives of this chapter are to learn more about relative humidity, terminal velocity, and ratios. Let's start with the first question. A cumulus cloud forms in the updraft of a convective circulation over warm ocean waters. The sea level temperature is 10 degrees Celsius and the relative humidity is 65%. Determine the mixing ratio of the air at sea level. For this question, you are going to want to find Table 6.3 in your textbook. It is also shown on this slide. On Table 6.3, find the temperature of 10 degrees Celsius on the table and note that your saturation mixing ratio over water is 7.76 grams per kilogram. Since you have the mixing ratio at 10 degrees Celsius, which is 7.76 grams per kilogram, and the relative humidity of 65%, you can find the mixing ratio of air at sea level. You want to multiply 7.76 grams per kilogram by 0.65, which is 65%, which gives you the mixing ratio of 5.04 grams per kilogram. For the second part of question 1, the air ascends and cools at the dry adiabatic rate, eventually becomes saturated, and a cloud forms. Use the Stuve diagram, which is figure 6.24 in your textbook, to determine the approximate altitude where the relative humidity of the ascending air equals 100%. Saturation can be determined from the Stuve diagram where the temperature from the dry adiabat intersects the initial mixing ratio line. You're going to want to find figure 6.24 in your textbook. It should look like the figure shown on this slide. Start at the temperature given, which for this problem was 10 degrees Celsius. It is shown in the red circle on this slide. Now follow the red line, which is the dry adiabat line, that goes up from 10 degrees Celsius, and find where the red line meets the black line, which is the saturation mixing ratio line. Finally, go straight over from where the red and black line meet, which is shown as the black dot, to the left axis, which will give you the altitude. In this case, it'll be 1 kilometer. So you will answer the second part of question 1 as 1 kilometer. Let's move on to question 2. Within a cloud at a temperature of negative 30 degrees Celsius, the saturation vapor pressure surrounding a supercooled water droplet is 0.51 millibars. Look at figure 6.10 for more information on this. And the relative humidity is 100%. What is the relative humidity of the air surrounding an ice crystal in the same cloud? To answer this question, first look at Table 6.2 in your textbook. Then find negative 30 degrees Celsius. Reading the table, it shows that at negative 30 degrees Celsius, over water the saturation vapor pressure is 0.51 millibars, and over ice the saturation vapor pressure is 0.38 millibars. Now you will want to divide the two, with the water value on top and the ice value on the bottom. This will give you 0.51 millibars over 0.38 millibars, giving you an answer of 1.34 or 134%. This is over 100%, so it is supersaturated. Therefore, you'll answer this question 134% and supersaturated. Moving on to question 3. What is the dew point in radiation fog at a temperature of 9 degrees Celsius? You'll want to ask yourself, what is the relative humidity of fog? Is it saturated? What would this make the dew point? Remember, when something is saturated, the temperature and the dew point are the same. Now for question 4. Suppose that a cloud droplet has a terminal velocity of 1 centimeter per second. If the air is calm, which means no updrafts or downdrafts, how long would it take for the cloud droplet to descend from the cloud base through a vertical distance of 4,000 meters? First, we are going to want to convert centimeters per second to meters per hour, since the height given is in meters and the answer is asking for hours. The process for conversion is given on the slide. Let's not get too nervous about all the math shown on this slide. We'll go through it step by step. First, let's convert the seconds to hours. Take 1 centimeter over 1 second and multiply it by the conversion of seconds to hours, which is 3,600 seconds over 1 hour, since there are 3,600 seconds in 1 hour. The seconds will cancel, and multiplying across, it gives you 3,600 centimeters over 1 hour. Next, let's convert centimeters to meters. You'll want to take 3,600 centimeters over 1 hour and multiply it by how many meters are in centimeters. You want to cancel out centimeters, so for the conversion, centimeters will go on the bottom and meters will go on the top. Since there are 100 centimeters in 1 meter, you have 1 meter over 100 centimeters. The centimeters will cancel. Multiplying across, you get 3,600 meters over 100 hours, which gives you a converted answer of 36 meters per hour. Lastly, you will want to take the height given, which in this problem was 4,000 meters, and divide it by your conversion of 36 meters per hour. This will give you a final answer of 111.11 hours. Over that time, it should evaporate in dry air. Therefore, you would answer this question 111.11 hours. For the last question, as a very general rule, 13 centimeters of fresh snow melts to 1 centimeter of liquid water. The density of fresh water is 1 gram per cubic centimeter, so the average density of fresh snow is 0.08 gram per cubic centimeter. Determine the density of snow if instead the ratio of snowfall depth to meltwater depth is 5 to 1. Since the ratio of the very general rule was 13 centimeters to 1 centimeter, dividing it out, 1 divided by 13 gives you 0.076 grams per cubic centimeter or 0.08 grams per cubic centimeter. So this shows that when you take the ratio that they gave you, which is shown on the math on the slide, 1 divided by 13, gives you the gram per cubic centimeters that they got. So let's do that with the ratio that we're given, which is 5 to 1. We were given a ratio of 5 to 1, so divide 1 by 5. This gives you 0.20 grams per cubic centimeters. So you would answer this question 0.20 grams per cubic centimeters. Remember to always divide the ratio. This ends the Chapter 7 math video. As always, if you have any questions, please let me know. I'm here to help. Have a great week.